Last video, we talked about linear, nth order, homogeneous, constant coefficient differential equation. And remember, we were doing the homogeneous case because there were two cases. We're talking about differential equations generally of that form. That's the most general linear differential equation. We have said we're going to restrict ourselves to constant coefficient ones. Last video, we looked at phi of d operating y equal to 0, homogeneous ones. It's now time to come back and look at non-homogeneous ones. All right, so the right-hand side is no longer 0. The first question that would come to mind is, since I do know how to solve this one through the auxiliary equation, is it going to be useful to have that? And the answer is yes. There's a theorem that says a general solution of phi of d operating on y equal to f of x is composed of two pieces. Y of x equal to one called y sub h of x and one called y sub p of x. Where y sub h of x is a general solution of the associated homogeneous equation phi of d operating y equal to 0 and y sub p of x is any particular solution of the non-homogeneous equation so a general solution of this equation is obtained by finding a general solution of that, a particular solution of this, and adding them together. So clearly, what we've done before is useful. We need a general solution of this to find a general solution of this. Now, there's a proof in the book. Right? To prove that this is a general solution, you'd have to prove three things. 1, it's a solution. 2, it's got the requisite number of parameters. And 3, it contains all solutions. 2 of those are obvious. Is this a solution of this? If you put that here, you'd have y sub p plus y sub h. And it's linear, so you take this one times this one times this one. But this one times this one is f. This one times this one is 0. Therefore, it satisfies. Does it have the requisite number of constants? Yes. This is a general solution of that. Therefore, it has to have the right number of arbitrary constants. And if this is an nth order differential equation. The last part is not that hard to prove, but I'm not going to do it like you read in the book, is to prove that every solution of this equation can be written this way. And that is not too hard to prove. All right? So it breaks down to then, want to solve this differential equation is solve this one, get its general solution, like in the last section. Find any particular solution that you can and add the two together, you're done. So we're going to concentrate then on finding particular solutions. Because we know how to find the y sub h. We're concentrating on finding a particular solution. Particular solution means, again, no arbitrary constants in it. Any solution will do. I thought of something when I was writing this down, is a general solution. I've seen many books replace that with the word the. And I really, really don't like that. Can you think of why I prefer the word a as opposed to the word the? To me, the word the somehow suggests uniqueness, that it is the one and the only general solution. And that's not true. You give me any differential equation, and I can produce an infinity of general solutions. So that's why I prefer the word a as opposed to the word the. All right, so finding a particular solution. There are a number of methods for doing that. We're only going to study one, but I'll at least mention finding y sub p. I'm going to list here some methods, and if you feel so inclined, you can look them up. One is undetermined coefficients. This is the only method that we're going to study. There's another method called annihilators. It is much like this one, very close to it. Then there's one called operators. It is in the textbook. If you want to learn it, if you want to learn any of these, I have no objection whatsoever. Right? Yeah, put it in the textbook because mechanical engineers told me once upon a time they like this method. So I included it in the book. But you're not responsible for it. You want to learn it? Fine. But you don't have it. And four, another method is called variation. Variation of parameters. These two basically work on the same problems. This one works on the same problems as well. This one is more general. It's more difficult to employ, but it's not subjected to the restrictions that these three have. And I'll tell you what they are in a moment. This one is more wide open. If these guys don't work, then you would have to use that one, right? So it is more general, but it is more difficult to put into effect. So we're going to study undetermined coefficients. The three of those, the operators, the annihilators, and the operators, only apply to the following functions. Polynomials, which is saying, therefore, no square root x's, no log x's, right? None of those, right? But it will handle e to the ax. It will handle exponential. It will also handle, I guess I call that in the book probably p, it doesn't matter, sine px and cosine px. Or any sum or product of those things. No other functions can be used. You can't use, say, tan, because tan is not the product of sine and cosine, it's the division of it. You can't use log, it's not in the list. You can't use square roots, you can't use cube roots. Right? You can only use these ones or these ones multiplied together. You could have x cubed e to the 7x cosine 4x. That would be a product of these things. Undetermined coefficients, annihilators, and operators will handle that thing. So I'm going to illustrate with a few examples to get the ideas going. Examples. Suppose I give you y double prime, 6y prime, minus 2y is equal to x squared plus 3. Now again, I'm going to concentrate on the y sub p. All right, so when I find my solution here, it's going to be, find, maybe say that, find a y sub p for this differential equation. So I'm not finding a general solution. I know if I wanted the general solution, I'd have to go solve the auxiliary, write down the y sub h, and then add to what I got here. But I'm concentrating only on the y sub p. All undetermined coefficients is intelligent guesswork. That's all it is. It's saying, what would you do? What would you think? Something to put here, so that when I differentiate it twice, and I differentiate it once, and I just put it there, and I do all of this, I'd end up with x squared plus 2. What do you think might it be? Well, I don't think it's an exponential. I don't think it would be tries. I don't think it would be square roots. The only logical thing is, if I put something that looks like that, and I differentiate it twice and once and put it there, it would come back again. So I think I'll put an ax squared. I think I'll put a c here. There's no x's there, but I think I'm going to put in some x's. Because x's would also give me those kinds of things, all right? Just to be safe. I don't know whether I need this. I don't know whether I need that. I for sure know I need this. Why? Because that one is going to give me x squareds, and I need x squareds. Therefore, I've got to have some x squareds. These two, I don't know. If I need them, I'll find them. If I don't need them, they'll turn out to be 0. But I'm being silly. So we say, assume that y sub p looks like this. And so what we're now going to do is determine these coefficients, a, b, and c. Hence the name undetermined coefficients for the method. So substituting, we need the second derivative, 2a. We need 6 times the first derivative, 2ax plus b. And then we minus 2 times that thing, ax squared, bx plus c. Must be equal to x squared plus 3. All right. Now I'm going to do something now, because I want to ask you a question. In practice, when I do this problem, I will not write the next line. But I want to ask you a question, just to make sure that ideas are straight in your mind. I'm going to take this left-hand side, and I'm going to gather all the x squared terms together. I'm going to gather all the x terms together, and I'm going to gather together all the non-x terms. Well, there's only one with ax squared. That's the, or ax squared, that's that one. And for x's, I've got this one, 12a, and I've got minus 2b. That's the x terms. And then I've got the non-x terms, 2a here, 6b here, and minus 2c equal to that. I'm now going to do the following, and you're going to tell me why I could do it. I'm going to equate the coefficient of x squared on this side to the coefficient of x squared on the other side. I'm going to equate the coefficient of x on the left side to the coefficient of x on the right side. I'm going to equate the non-coefficient of x terms to the non-coefficient, right? I'm going to do that in a minute. But I'm going to ask you, by what authority can I do that? You know, if I write down the following equation, 2x squared plus 3x minus 4 is equal to 5x squared plus 6x plus 7. Let's equate coefficients. 2 equals 5, 3 equals 6, and minus 4 equals 7. Yeah, that's just wonderful. So why can you do it here, but you can't do it there? And don't tell me because there's a's and b's and c's. It's the same principle. I'm equating coefficients. Why can I do that here? Say that one must be equal to 1, that one must be equal to 0, and that one must be equal to 3. How come I can do it here but not there? What's the difference? Answer. For how many values of x is this equation true? Answer, 2. basically, it's a quadratic equation. If I brought all the x squares together, the x's together, the constant, I'd have a quadratic equation, and there would be only two values of x for which it's satisfied. For what values of x is this supposed to be true? Answer, all of them. Whatever interval I'm working on, and perhaps here I'll be saying I want the solution from minus infinity to infinity. This is true for all x. I want it to be true for all x's. And notice then I can do the following. If it's to be true for all x's, I'm going to put in x equal to 0. You're gone, and therefore you're gone, you must be equal to you. That's got that one equal to that one. I can then turn around and differentiate this thing and put in x equal to 0. If I did that, I would get this one must be equal to 0. And if I differentiate it again, I would get this one must be equal to that one there. That kind of thing you did in first year when you did partial fractions. I just wanted to remind you of the difference between this and this. So we equate coefficients. And as I said earlier, I don't have to write this line to do that. I could have taken this line and said, let's now equate coefficients of x squares, x, and non-x terms left and right, without writing them all together. I could have done that. And therefore I would have, for x squared terms, I would have minus 2a equal to 1. For x terms, I would have 12a minus 2b is equal to 0. And for non-x terms, which I call 1, I would have 2a. And 6b minus 2c is equal to 3. And what have you got? 3 equations in 3 unknowns to solve for a, b, and c. Any way you want. Hey, those are linear. 12, 10, here I come. I got multitude of methods of solving linear systems in first year. I could do augmented matrix. I could do Cramer's rule. I could do matrix inversion. I know you will not do any of those, and neither would I here. I solved this one for A. I put it here. I then solved this one for B. I put the A here. I put the B here, and I solved for C. I leave you to do solve for A, B, and C any way you want. And now you've got your particular solution. Solve it, put the A here, the B here, and the C here, and you will have your particular solution. Get the idea of how it works? Well, let's change. Let's leave the left-hand side the same and put some different things on the right-hand side. Suppose I put on the right-hand side 3 cosine 4x. Now remember, undetermined coefficients is simply intelligent guesswork. So you're thinking about, what would I put here? So if I differentiate it twice, and then do this, and do this, it might give me cosine 4x. Well, I'd be willing to bank on that I probably need a cosine 4x. Certainly if I differentiate this twice and put it here, I'm going to get cosine 4x. But if I differentiate this once for here, I get sines. And there's no sines here. Maybe I need some sines here also. Now you can add anything else you want. And if you don't need it, the coefficients will turn out to be 0. Right? But I feel I'm pretty safe saying, I think a particular solution would look like that. So let's substitute. What do we need? The second derivative, minus 16a cosine 4x, minus 16 16b, the sine of 4x for 2 derivatives, plus 6 times minus 4a sine 4x plus 4b cosine 4x minus 2a cos 4x and b sine 4x. That's supposed to be equal to 3 cosine 4x. Equating coefficients. By the way, I just thought of another reason why we can equate coefficients. Should have mentioned it in the last example. Darn it. Remember what I did in the last example? We gathered the x squares on the left. We gathered the x's on the left. We gathered the constants, and we had over here x squared plus 3. And I convinced you, at least I hope I did, that I could equate coefficients, right? And I said the reason is because this is supposed to be true for all x's. Let me show you a different way. Suppose I take this one and I bring it over here, in which case I'd have that. Let me bring this one over here, in which case it would be minus 3 here. And now on this side, it's a 0. So what have I now got? I got A's and B's and C's, A's and B's and C's, and A's and B's and C's, and a couple numbers in here, and this adds up to 0. Why do the coefficients have to be 0? One word, 2 words. Linearly independent. The functions x squared and x and 1, if I think of a 1 here, are linearly independent functions. The only way, then, that you could have a constant times one of them, plus a constant times the other, plus a constant times the third, if all 3 constants were 0. That gets me back those same equations that I had a minute ago. And the same thing would be true here. If I gathered all of the cosines together, I gathered all of the sines together, on the left-hand side, put it equal to 0, the only way those coefficients could be 0 is if they're both 0. I mean, if the only way the equation to be satisfied, both conditions, both coefficients would have to be 0 because cos and sine are linearly independent. But we simply say equating coefficients. So for the cosine terms, I have minus 16a here. I have plus 24b's here. And I have minus 2a's there, and equal to then 3. And for the sine ones, sine of 4x, I have minus 16b's. I have plus, I thought I remembered saying 64. No, 24. Good thing, all right? 24. Minus 24, we're doing sines. Minus 24a. Sines, minus 2b is equal to 0. So what do you got? 2 linear equations and 2 unknowns. Solve them any way you want. You can probably bring these together. Then you can say solve this rate in terms of b, put it into here, and so on. But solve, right? Solve. Any way you want. Are these equations always going to be linear when you use undetermined coefficients? The answer is yes. You'll always be confronted with a system of linear equations. How you solve them is up to you. Next example, change then the right-hand side again. I'm going to change it to 3x e to the minus 2x. So this time is different than the previous two. The first one was a polynomial, and the second one was a tree. This has got an exponential, but it's also got some x in front of it. Because remember I said over there what the determinant coefficients would handle. It'll handle polynomials, exponentials, sines and cosines, sums of those things, and products. Maybe we should put in a sum here. How about we also put in here plus x, okay? Just so we see a sum as well as a product. So assume. What are we going to assume? Well, for this one, I think I'm going to go like that first example, put ax plus b. That would correspond to what we did in that first example. For this one, I think I'm going to put a cx e to the minus 2x, because that certainly differentiated leads to that thing back again. But I can also envisage when I differentiate this thing and I put it here, that x is going to go away, leave me only those. Maybe I'll put here that, just in case I need it. Maybe I don't, maybe I do. So I'm going to assume that for my particular solution, right? All right, substitute. We need the second derivative. Second derivative of u, gone. Second derivative of this. Remember that rule I told you about for differentiating a product twice? Remember that rule? It said, you bypass the c. To differentiate this twice, you take the second derivative of him and no derivative of him. That's gone. Second derivative is gone. Then twice the first derivative of each. Minus, differentiate him, gone, differentiate him. Okay, 4 e to the minus 2x. That's first of him, doubled. And then this one times the second of him, 4 e to the minus 2x. Then, that's the second derivative of this. Then I need the second of him plus 4d e to the negative 2x. So you're like, there then is y double prime. Then we need 6. First derivative, a. First derivative, c e to the negative 2x minus 2cx e to the minus 2x. And then minus 2d e to the minus 2x. How does that look for the first derivative? And then we finally need minus 2 times the function. That's supposed to be equal to then 3x e to the minus 2x plus x. If we equate coefficients, let's see what we get. We equate coefficients, we have x e to the minus 2x terms, we have e to the minus 2x terms, we have x terms, and we have constant terms. So for the x ones, that 4c, x, that one, minus 12c, minus 12c. And we have another one here, minus 2c, is equal to 3. E to the x's. Here, e to the minus 2x, minus 4c, minus 4c. Got that one. Here's one. 4 Ds. Okay, here's one. 6 Cs. Here's one. Minus 12D. And finally, there should be one down in here too. Minus 2D. Minus 2D is equal to, on the right hand, 0. X's. Nothing in there, there, nothing, nothing, nothing. There. Minus 2A. Minus 2A. And X is on the right, 1. Constants. 6A. And 2B equal to no constants on the right. So what do we get? As kind of predicted before, 4 equations and 4 unknowns. But notice them, they occur in blocks. From this guy, you had these 2 terms, and so you get a pair of equations in those 2 coefficients. This term led to these 2, which are different than those 2, and you get the AB equations down here. So although it's 4 equations and 4, no, it's really 2 and 2, 2 and 2. So you solve those again. All right. Getting the idea of undetermined coefficients? Well, instead of me guessing all the time, let me show you a rule that encompasses everything that we've seen in these examples. It says, if a term of f of x, that's the right-hand side, consists of a power, an exponential, a sine or a cosine, or any product thereof, assume as a part of y sub p a constant multiplied by that term plus a constant multiplied by any linearly independent function arising from it by differentiation. That rule encompasses what we see before. In particular, right? In particular, if I simply look at this one, it would say, you see that? You should put ax e to the negative 2x. You should then differentiate that. And if you get anything new meaning linearly dependent, put a constant in front of it. If I differentiate this, I take this one times the derivative of that one. That's not new. It's minus 2 times that. But if I take this one times the derivative of that one, I get e to the negative 2x. That's different than that. So I put a constant in front of it. That's those 2 guys. Right. And then I take this one, and I say, I need a constant in front of you. And if I differentiate x, I get what? That's different. I need a t. That's those 2 terms. Got the idea? Right. So all you have to do is do that. Follow that rule. But you might guess, because it says rule 1, it doesn't say rule, there's probably another rule. And that is true. Rule 1 does not always work. We need rule 2. But there are only 2. And we'll look at rule 2 next time.